Hello, College Algebra. We're moving on to Chapter 5 to finish this semester. Chapter 5.1 starts with this topic of inverse functions. So we haven't talked about this yet. The notation for an inverse, here's a function f of x plus 7. The notation for an inverse function is f inverse of x. You put this little -1 symbol up here. Now, it's up here like it's an exponent, but it's not an exponent. It's not an exponent. It's an inverse function notation. I like to say that the inverse function undoes. I like to use this phrase, if that's a word, undoes the function f. So an inverse function undoes whatever f does. So watch this. This is really easy. Some of these basic ones are easy. So if you got this function x plus 7, then what would undo that? The inverse function would take an x and subtract 7. If you've got this function that's x times 6, I guess the inverse function for g would be x divided by 6. Yeah, I guess if this function is h and it takes x and cubes it, x to the third power, x cubed, the inverse function would undo that, would cube root it. Cube root the x. So on a basic level, that's cool. Now when the function has 2 or 3 steps involved, or more, it takes a little more thinking. I still want to teach you this. I came up with this method called the Smith method. I called it the Smith method. And what I want to do is I want to write down what f does. So I'm writing down what f does to this x. So there's a new function here called f, different. And this is a new function. It's got a couple steps. Let's see. If you plug an x in, imagine plugging an x in, you would multiply by 4, and you would subtract 3 in that order. So, because it's kind of about order of operations. So let me see. Let me write that down. Multiply by 4, and then subtract 3. Okay, so to come up with the inverse function for this, what I want to do is I want to do the opposite of those steps, in the reverse order. I want to undo whatever f does. I want to do the opposite of these steps in the opposite order. So I start at the bottom, and here's what I do. I put an x out here, and I start doing stuff. So I'm going to do the opposite of that. I'm going to add 3. Next, I'm going to divide by 4. Whenever you do the next step, you do it to the whole thing. So I'm dividing the whole thing by 4. So there it is. There's the inverse function. And we just did the Smith method. The Smith method. Just write that in. The Smith method. Maybe it'll become famous. Anyway, there is a book method. There's a different way to do this. Let's try this other way too. So let's just do this same function here. This function is 4x minus 3, and we found the inverse function using the Smith method. But there's another method. The book, I call it the book method. Here's what they do. Step 1, switch x and y. Let me just write something here. This is how to find an inverse function. How to find f inverse. So step 1, switch x and y. Step 2, solve for y. So that's a good method. It works. In fact, the Smith method doesn't always work. There's a couple places where it doesn't work. But this is cool. So let's try that. Switch x and y. Switch x and y. Okay, that's y. Oh, that's y? So call it x. That's x, so call it y. That's what we mean by switch x and y. And now solve for this new y, and this new y will be f inverse of x. So what will I do to solve for? I'll add 3. I'll add 3, of course. And then I'll divide by 4. Yeah, okay, same thing, right. And this new y is not the old y, f of x. This new y is the switched y. It's f inverse of x. So, you got a couple methods to try to find an inverse function. There's a lot of concepts about an inverse function. It's about graphing an inverse function and There's a lot of cool concepts. I'm going to keep talking here. You know, I'm going to get rid of these notes. You know, there's this function here called f of x. If I made a little chart and was plotting some points for this function, you know, let's just try something. Plug in a 0, what do you get? You get -3 for y, that was easy, right? Plug in a 2 for x, and you get 5. Doing a little, plotting a few points, just for fun. Plug in a 4. 4 times 4 is 16, minus 3 is 13. I plugged in a 4, I got 13. So that's true. Now, what happens if I make a chart for f inverse? Let's just make a little chart here, different chart for f inverse of x. I mean, he's a different function. It's a different function. Sometimes I like to call them cousins because they're related to each other, but it's a different function. Let's just see, I don't know, let's just plug in some random stuff. Let's plug in a -3 for x. If I plug in a -3 for, oh, wait a minute, that's a 0 over 4. 0 over 4, that's 0, okay. Let's just plug in a 5 for x. By the way, here it is too, you know, this was the same function here. We plug in a 5, 5 plus 3 is 8 over 4, that's 2, okay, all right. I don't know, I'm just picking some random numbers here. Let's try a 13, let's plug in a 13. 13 plus 3 is 16 divided by 4, the answer is 4. Ah, do you notice anything? Well, this is true for all inverse functions, and not just for these numbers. The chart, the x's and y's of the original function are the same x's and y's all switched for the inverse function. The x's became the y's became the new x's. Remember the phrase, we switched x and y? That's part of it. Now, so that's true. That wasn't true for that one example. That's true for all inverse functions. It's kind of a cool concept. And then that leads to this concept. Check this out. Now, what was that? Hang on. What was that original function there? 4x minus 3. Okay. And here it was. And if I was to graph that, I could plot these points. 0, -3, 2, 5. It's kind of a steep one here. Anyway, it's a line. It goes through these points. So this is a picture of f of x. If I was to plot this f inverse of x, there's some points to plot there. And just for fun, remember what it was? It was x plus 3 over 4. Is that what it was? And if I plot those points, -3, 0, hang on, -3, 0, that's this. Oh yeah, it's that point reversed. Yeah. Remember this point was 2, 5? Well, this point was 2, 5. This point on this function is 5, 2. So it's 1, 2, 3, 4, 5, 2. Right, it's that point reversed. 13, 4, let me try that. X is 13, that's a 5, oh boy. 13, 4. All right, if I connect those dots, this is a line. Hey, not bad. And that's the inverse function. And now you're supposed to notice something, because this is always true for inverse functions. You're supposed to notice that they are mirror images of each other. There's some symmetry here. They're mirror images of each other, but the mirror is kind of funny. The mirror is this diagonal line. The mirror is this diagonal line right here. Right? The perfect diagonal line right there at a 45-degree angle. It's called y equals x. That's the mirror. And they are mirror images or reflections around this diagonal mirror. And that's true for all inverse functions. Just this is one example. Yeah. So when this one comes in and hits the mirror, the other one comes in and hits the mirror. When he breaks through to the other side of the mirror, he breaks through to the other side of the mirror. They're mirror images of each other. So that's a visual concept that kind of based on this switching x and y concept is what that comes from. All right, I'm going to keep talking just a little bit. get rid of this great picture. So now that you know those, these are all concepts about inverse functions. And so now look at this graph. So here's I'm going to make up a function here. Here's a function. So there's a function, f of x. And now, hopefully you've had art class. Can you please draw the inverse function? Can you please draw the inverse function? Remember, it's a mirror image. And where's the mirror? Hang on. The mirror is this perfect diagonal. By the way, I called this thing a function. Is it really a function? Does it, remember, does it pass the vertical line test? Yeah, I think it does. I think it's a function. All right, I'm going to try to draw its inverse function. Here I go. Oh boy, this is tricky. You know, where he crosses the x-axis, this one's going to cross the y-axis. You know, he comes in here, he gets real close to the mirror, and then he goes away. Oh, then he crosses the x-axis again. So this one's going to cross the y-axis. Then he takes a little bend that way. Okay, I think I'll bend that way. Hey, I don't think I'm doing too bad. It comes up here and crosses the y-axis. Well, that means mine's going to come across the x-axis. It sort of bends toward the mirror here. It's going to cross through the mirror, come out the other side. Wow, that was fun. That ain't bad. That's F inverse. I'm impressed. Let me ask you this conceptual question. Is F inverse a function? And the answer is no. It fails the vertical line test. Maybe you can see that. It fails the vertical line test. All right, so that's an issue. And that starts to get a little complicated. The reason F inverse failed the vertical line test is because the original function, which was a function, it passed the vertical line test, but it failed the horizontal line test. So the original function needs to be one-to-one. That's a new phrase, one-to-one. If the original function is one-to-one, here's what that means. It means the original function passes the horizontal line test. Mine didn't, but this is, I'm saying it, if the original function is one-to-one, what that means is it passes the horizontal line test. It means for every y, there's one x. Or for every x, there's one y. That's what it meant to be a function. Now, for every y, there has to be one x. It has to pass the horizontal line test. And if it does, then the inverse function will pass the vertical line test. And therefore, the inverse function is a function. See, what we have in here is not actually not a function. I probably shouldn't be using that notation. It is an inverse relationship. I have an inverse relationship on the board here. The pink graph is the inverse of the black graph, but it wasn't a function. And this, so there's these concepts. If the function is one-to-one, that means that's a new concept. It passes the horizontal line test. That means its inverse will pass the vertical line test, and that means its inverse is a function. And we tend to worry about that. So you'll have some exercises at the beginning of the homework that'll ask you, they'll give you a picture and say, is that a one-to-one function, or does it pass the horizontal line test? The answer is no. By the way, that's good old x squared. You know, you might think the inverse of x squared is the square root. And it is the square root, but you can see it's a little incomplete, right? If you actually turn this thing sideways and looked at his inverse, it would be this, which is not a function. You know, if this is y equals x squared, when you switch, you get x equals y squared. And when you solve for y, you get the plus and minus square root of x. So that's the issue. That plus and minus causes the issue. But we're starting to hit the edge of pre-calculus here with this deep theory here about inverse functions. So to me, my homework's not too hard, I don't think. It's about finding an inverse function, which we did the first chunk of this video. And now, at the beginning of some of the homework asks you about passing the horizontal line test. Is the function 1-to-1 and pass the horizontal line test? It's pretty easy visually. All right, do some homework. Thank you.